And welcome back. As we continue looking at the interstellar medium, we of course previously looked at some of the interstellar dust that comprises some of the different things, but let's go ahead and take a little bit more of a fine-tooth comb to some of the cosmic dust that comprises of our universe. So let's start first by looking at some of the voids in space. This image shows an example of what is a common sight through large telescopes, a dark region on the sky that appears to be nearly empty of stars. And for a long time, astronomers have debated whether these dark regions were empty tunnels through which we look beyond the stars of the Milky Way galaxy into intergalactic space, or whether they were clouds of some dark material that actually block the light of stars beyond. Well, what this was is that we were actually on the trail of being able to detect dust. Dusty clouds in space betray their presence in several ways. The first is by blocking the light from distant stars, by emitting energy in the infrared part of the spectrum, by reflecting the light from nearby stars, and by making distant stars actually look redder than they really are. That dark cloud, of course, that we just saw actually blocked the light of many of the stars that were lying behind it. You'll note how the regions in other parts of the photograph appear to be very crowded with stars. Such opaque clouds are conspicuous on any photograph of the Milky Way galaxy. The dark rift that appears to run lengthwise down a long part of the Milky Way in our sky and almost appears to split in two is actually produced by a collection of such obscuring clouds. While dust clouds are typically too cold to radiate a measurable amount of energy in the visible part of the spectrum, they do glow brightly in infrared. Now, the reason for this is that small dust grains absorb visible light and ultraviolet radiation very efficiently. These grains are heated by absorbed radiation, typically in temperatures that range anywhere from about 10 to 500 Kelvin, and then re-radiate this heat at infrared wavelengths. Now, due to their small size and low temperature, interstellar grains radiate most of their energy at infrared to microwave frequencies, with wavelengths ranging from about 10 to hundreds of microns. Now, Earth's atmosphere is opaque to radiation at these wavelengths, so emission by interstellar dust is best measured from space. Observations that actually come from above Earth's atmosphere show that dust clouds are present throughout the plane of the Milky Way. And here we can see a comparison between two different views of that dust. The Horsehead Nebula is a large cloud of dust that fills the lower part of this image here. In image A, we can see in visible light the dust clouds are especially easy to see against the bright background. You'll also note that in infrared, the regions that appear dark in visible light appear actually a lot brighter in infrared. And this is because the dust is heated by nearby stars and re-radiates this heat in the infrared, such that only the top of the horse's head is visible in the infrared image. The bright dots that we see in the nebula below and to the left and at the top of the horsehead are actually young, newly formed stars. And here is another example of how the cosmic dust might appear differently. This infrared image is actually showing a field in the plane of the Milky Way galaxy. Now, normally this image is a very dark band that doesn't really look like much is there. But this emission is actually being produced by tiny dust grains which emit anywhere about 3.6 microns or blue, 8.0 microns green, or 24 microns, which is red. The densest regions of dust are so cold and opaque that they do appear as dark clouds even at these infrared wavelengths. The red bubbles visible throughout it really kind of indicate to us regions where dust has been warmed up by young stars. This heating increases the emission at 24 microns, leading to the redder color that we see here in this image. And so let's take a look at the reflection nebula. Some dense clouds are close to luminous stars and scatter enough starlight to become visible. Such a cloud dust, illuminated starlight, is called a reflection nebula, since the light we see is actually starlight that's been reflected off of grains of dust. And one of the best known examples of the nebulosity around each of the brightest stars is in the Pleiades cluster. Here the dust grains are small, and such particles actually turn out to scatter light with blue wavelengths much more efficiently than light at red wavelengths. Therefore, a reflection nebula usually actually appears bluer than that of its illuminating star. And we can see that here in this image how that property would work. The bluish light surrounding the stars in this image, of course, are an example of a reflection nebula. The nebula shines only because the dust within it scatters light from a nearby light source. So the Pleiades cluster is currently passing through an interstellar cloud that contains dust grains which scatter the light from the hot blue stars in the cluster. Now, the Pleiades cluster is about 400 light years from the Sun, just to give you some context of the distance that we are looking at here. Now, of course, even though that was much more blue, most of the time we see interstellar reddening occur. The tiny interstellar dust grains absorb some of the starlight they intercept. But at least half of the star that interacts with it is the grain that's merely scattered, that is redirected rather than absorbed. Now, since neither the absorbed nor the scattered starlight reaches us directly, both absorption and scattering make the stars look dimmer. The effects of both of these processes are what we refer to as interstellar extinction, because that light is forever lost to us. Now, astronomers first came to understand interstellar extinction around the early 1930s as to explain a puzzling observation. In the early part of the 20th century, astronomers discovered that some stars look red even though their spectral lines indicate that they have to be extremely hot and thus should look blue to us. The solution to this seemingly contradiction that they observed turned out to be that the light from these hot stars is not only dimmed but also reddened by interstellar dust, a phenomenon that we now refer to as interstellar reddening. So it's effectively shifting the wavelength of light so that way we are only seeing the red wavelengths. Now, dust does not interact with all the colors of light in the same way. Much of the violet, the blue, and green light from these stars has been scattered or absorbed by dust, so it does not actually reach us here on Earth. Now, some of their orange and red light with longer wavelengths, on the other hand, it more easily penetrates the intervening dust and completes its long journey through space to enter the Earth-based telescopes. Thus, the star looks redder from Earth than it would be if you could see it from nearby. In the most extreme cases, stars can be so reddened that they are entirely undetectable at visible wavelengths. It can only actually be seen, then, at the infrared or longer wavelengths. And of course, you can imagine how this might start interfering if we want to start doing stellar surveys of different parts of space, because if you're not in the visible spectrum, now we also need to look at the infrared. And so let's take a look at how this actually would play out with a little more visual example. We have all seen an example of reddening here on Earth. For example, if we look at our own sun, it does appear to be much more redder at sunset than it does at noon. And part of the reason is that the lower the sun is in the sky, the longer the path its light must travel through the atmosphere. Now, over a great distance, there's a greater chance that sunlight will be scattered. Since red light is less likely to be scattered than blue light, the sun appears more and more red as it approaches the horizon. And again, you can see that here in this image as light from a star is traveling. You see the blue light has much shorter wavelengths, and so it is more likely to hit a particle and then bounce off away from the observer, whereas the red light has the ability to pass through that due to its longer wavelengths. And lastly, that's going to get us to this idea of interstellar grains. So why isn't it that the interstellar gas that reddens distant stars and not the dust? Because, well, we know that the gas is typically much more abundant. Well, keep in mind that atomic or molecular gas is almost transparent. Even in Earth's own atmosphere, the very high density when compared to that of interstellar gas is still relatively transparent. That's the reason why we can look up through our sky and see things. Now, the quantity of gas required to produce the absorption of light in interstellar space that we are seeing would actually have to be pretty enormous. In fact, the gravitational attraction of so great a mass of gas would affect the motion of stars in ways that we could easily detect if it was gas that was causing all of this interference. Now, such motions are not observed. Therefore, interstellar absorption cannot be the result of the interstellar gas, even though most of that space that we're looking at is interstellar gas. Now, although gas does not absorb much light, we know from everyday experience that tiny solid or liquid particles can actually be a very efficient absorber. Think about dust storms, smoke, smog, and other examples of things that absorb light. Think about, whether it's a piece of fabric. These things are all good absorbers of light. And you might think about what are these particles made of and how do they form to actually have this property of absorbing lengths of light? Well, if we start looking after hydrogen, helium, the most abundance in our universe turn out to be oxygen, carbon, and nitrogen. These three elements, along with magnesium and silicon and iron, turn out to be the most important components of interstellar dust. Grains of interstellar dust are found in things such as meteorites and can be identified because the abundance of certain isotopes are different from what we see in other solar system material. And so here's a visual example of an interstellar grain. The most widely accepted model has grains with rocky cores that are rich in either carbon or rich in silicates. In the dark clouds where molecules can form, these cores are typically covered by icy mantles. The most common ices, of course, are going to be things such as water, methane, and ammonia. The ice mantles are sites for some of the chemical reactions that produce those complex organic compounds that we discussed previously. Now, typical individual grains must be just slightly smaller than the wavelength of visible light. If the dust grains were larger than the wavelength light, then the starlight would not be reddened. So we are talking very tiny grains here in terms of what we see in space.